Welcome to this introduction to refrigeration. In this video, we'll explore the fundamental concepts of refrigeration, including the ideal refrigeration cycles, coefficient of performance, and common refrigerants used in the industry. We'll also take a closer look at real-world deviations from ideal cycles, helping you understand how practical systems differ from theoretical models.
The learning outcomes of this instructional video are: explain refrigeration in thermodynamic terms. Describe the reversed Carnot cycle and its difficulties in practice. Describe the reversed Rankine cycle as a simple refrigeration cycle. Define the coefficient of performance in refrigeration. Apply steady flow energy equation for different processes in a refrigeration cycle. Describe the units of measurement for the capacity of a refrigeration plant. Explain the typical refrigerants and the methods used to determine their properties. What is refrigeration? Heat flows in the direction of decreasing temperature, that is, from high-temperature regions to low-temperature ones. This heat transfer process occurs in nature without requiring any devices. The reverse process cannot occur spontaneously. Transferring heat from a low-temperature area to a high-temperature one requires a special device known as a refrigerator or heat pump. Therefore, refrigeration is the process of removing heat from a substance and lowering its temperature below the surrounding environment. Refrigerators facilitate this refrigeration process. How is the refrigeration brought about? Heat is transferred from one body to another using a fluid, commonly referred to as the refrigerant or working fluid. When the refrigerant absorbs heat from the cold body, it evaporates by primarily taking in the latent heat of vaporization and then releases this heat to the hot body through condensation. This process can be illustrated with a diagram. Heat Q1 is absorbed from a cold body at temperature T1 and released as heat Q2 to a hot body at temperature T2. Since this process requires external work, W, Q2 is equal to Q1 plus W. Let us now analyze the thermodynamic cycle associated with refrigeration. Let's examine the thermodynamic processes experienced by the refrigerant and how they are represented on a phase diagram. The refrigerant engages in a series of cyclic processes that involve both the absorption of heat from its surroundings and the subsequent rejection of that heat to another location. These processes are essential for the efficient operation of refrigeration systems, as they allow the refrigerant to continually cycle through phases of heat intake and release. The ideal performance cycle consists of two isothermal processes and two constant entropy processes, which are determined by the amount of heat absorbed from the cold body for each unit of work input. This cycle is known as the reversed Carnot cycle. At this point, let us take a closer look at the reversed Carnot cycle, as it is represented on an entropy temperature diagram. We will analyze the various stages of this cycle and their significance in the context of thermodynamics. It is important to understand the difference between the Carnot cycle and the reversed Carnot cycle. The Carnot cycle is an idealized thermodynamic process that establishes the maximum efficiency for converting heat into work. It comprises four reversible processes: isentropic compression, isothermal heat addition, isentropic expansion, and isothermal heat rejection. The reversed Carnot cycle operates in reverse, serving as a refrigeration or heat pump cycle. What are the steps involved in the refrigeration cycle, and how do they work? The diagram shows the components of the refrigeration cycle. Let us analyze the components involved in fundamental refrigeration processes. Initially, isothermal heat absorption occurs within the evaporator or cooler, where the liquid refrigerant extracts heat from the cold space and transitions to a gaseous state. Subsequently, the compressor performs isentropic compression, providing external energy that elevates the pressure and causes the refrigerant to reach a superheated state. Thirdly, the refrigerant circulates through the condenser, where it thermally dissipates heat isothermally to a heat sink, typically the ambient environment, allowing it to revert to a liquid state. Finally, the refrigerant experiences isentropic expansion through an expansion valve, returning to its original pressure. How can you assess the efficiency of a refrigeration cycle? The objective of a refrigeration cycle is to attain effective cooling while minimizing energy consumption. The thermodynamic efficiency of refrigeration systems is quantified by the coefficient of performance, COP. The coefficient of performance, COP, measures the cooling achieved per unit of work input, referred to as the refrigerating effect. Therefore, the COP is written as QL divided by Win, where QL is the heat transfer from the low-temperature body, and Win is the work input. Let's now derive the coefficient of performance in terms of temperatures. According to the first law of thermodynamics, QH equals QL plus Win. Therefore, COP is written as QL divided by QH minus QL. As shown in the TS diagram. T1 equals T4. We consider this as TL. Also, we know that according to the definition of entropy, delta S equals Q divided by T. Therefore, QL is written as TL into S1 minus S4. Similarly, we can write QH equals TH into S2 minus S3. When you look at the TS diagram, entropy changes in both instances are the same. So we take this as delta S. Substituting for QL and QH, we can finally obtain the COP as TL divided by TH minus TL. The reversed Carnot cycle is an idealized refrigeration cycle representing the maximum efficiency achievable in refrigeration processes. However, practical refrigeration systems face several limitations that render the reversed Carnot cycle unsuitable for real-world applications. The reversed Carnot cycle assumes isothermal heat absorption and rejection and isentropic compression and expansion, which are difficult to achieve in real refrigeration systems due to irreversibility in actual components. The compressor in a real refrigeration system cannot operate as a perfectly isentropic device due to friction, heat losses, and mechanical inefficiencies, leading to deviations from the ideal cycle. In the Carnot cycle, evaporation must stop at the point where the working fluid reaches a wet vapor state. However, achieving this precisely is not practical. The Carnot cycle requires an isentropic expansion process, which would require an expansion turbine, or expander. In real refrigeration systems, a simple throttling valve, or expansion valve, is used instead, which causes energy losses and reduces efficiency. The isothermal heat transfer processes in the Carnot cycle require very slow heat exchange to maintain constant temperature. This leads to impractically slow operation, making it unsuitable for real-world refrigeration applications. The reversed Rankine cycle closely resembles practical vapor compression refrigeration systems. Let's explore this cycle now. This refers to the reversed cycle of the Rankine cycle, which is commonly used in power generation processes. The two diagrams illustrate the simple or ideal reversed Rankine cycle in the temperature entropy and pressure enthalpy coordinate systems. Let us conduct a more in-depth examination of the reversed Rankine cycle. The reversed Rankine cycle is a more practicable thermodynamic cycle used in refrigeration analysis. It is essentially the Rankine cycle operating in reverse, utilizing external work to extract heat from a cold space and reject it to a warmer environment. In the ideal or simple cycle, The dry saturated vapor is compressed in the compressor, and the refrigerant is cooled to a saturated liquid. Why is the reversed Rankine cycle preferred? The reversed Rankine cycle is preferred over the reversed Carnot cycle for the analysis of refrigeration systems due to several practical and operational reasons. In the reversed Carnot cycle, when considered with two-phase substances, the compression process involves a wet vapor mixture, partially liquid and partially vapor, which can cause mechanical damage to the compressor. In contrast, the reversed Rankine cycle ensures that compression occurs only in the superheated vapor phase, preventing liquid droplets from damaging the compressor. The isothermal heat addition and rejection in the Carnot cycle require infinite area heat exchangers, which are impractical in real systems. The Rankine cycle simplifies heat exchange by using isobaric, constant pressure, processes, making heat exchangers more practical and efficient. Although the reversed Carnot cycle has a theoretically higher efficiency, its practical implementation suffers from higher irreversibility and difficult operating conditions. The Rankine cycle provides a realistic and efficient approach, balancing thermodynamic performance with feasibility. Let's examine work and heat transfer in the ideal reversed Rankine cycle and calculate the coefficient of performance, COP. We utilize the steady-state energy flow equation, which in thermodynamics represents the energy balance for a control volume in a steady-state process where system properties remain constant over time. This equation is especially valuable for analyzing devices like turbines, compressors, heat exchangers, pumps, and nozzles. The steady-state energy flow equation for unit mass between two state points is expressed as Q12 minus W12 equals change in enthalpy, plus change in kinetic energy, plus change in potential energy, as shown here. The equation that describes energy flow in a steady state can be applied to each part of the refrigeration cycle. We can assume that changes in kinetic and potential energy are minimal and can be ignored. This allows us to simplify our analysis by concentrating on the energy exchanges within the components without complicating factors from kinetic and potential energy changes. Initially, let us examine the compressor, wherein the process is characterized as isentropic, indicating the absence of heat transfer. We can obtain the work done on the working fluid as the change in enthalpy. The minus sign indicates that work has to be supplied externally. The next step is condensation, a constant pressure heat rejection process. Using the energy flow equation between state points 2 and 3, we can determine the heat rejection as the change in enthalpy, which yields a negative value due to heat being rejected from the working fluid. The next process involves constant enthalpy expansion through an expansion valve, wherein the pressure is reduced to match the evaporator pressure. By applying the steady flow energy equation, we can confirm that enthalpy remains constant due to the absence of work or heat transfer during the process. The final step in the cycle is constant pressure heat absorption in the evaporator. Using the energy flow equation for the evaporator, we can calculate the heat absorbed by the working fluid. Now, let's examine the COP of the reversed Rankine cycle. The COP is defined as the refrigerating effect divided by the compressor work, which can be calculated as H1 minus H4 divided by H2 minus H1. The capacity of a refrigeration plant, which refers to its ability to remove heat over time, is measured using several key units. Ton of refrigeration, TR. 1 TR is the heat required to be extracted from 1 ton of water at 0 degrees Celsius in 24 hours to convert it into equivalent ice at 0 degrees Celsius. British Thermal Units, BTU. In refrigeration applications, the British Thermal Unit, BTU, is also used for quantifying heat energy. A BTU is the amount of heat energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit at standard atmospheric pressure. Understanding the conversion between various unit systems is essential, as both systems are frequently employed in practice. Now, let's examine the deviations from the simple Rankine cycle observed in actual refrigeration cycles. Number 1. The liquid refrigerant in the condenser is subcooled, meaning it is cooled below the condensing temperature before passing through the expansion valve. This is advantageous as it enhances the refrigerating effect per kilogram of refrigerant. Number 2. Typically, the refrigerant exits the evaporator in a superheated state before entering the compressor. This superheating can happen in the evaporator coil while still within the cooled space, resulting in an increased refrigerating effect per kilogram of refrigerant. Pressure drops in both the evaporator and condenser are evident in practical cycles, as illustrated in the TS diagram of the actual refrigeration cycle. The process 123 shows the refrigerant flow in the evaporator, with point 3 marking its exit and the entry to the compressor. Superheating occurs as the refrigerant absorbs heat from both the evaporator and the suction pipe linking the evaporator discharge to the compressor suction valve. Additionally, there is a pressure drop at the compressor inlet from point 3 to 4, caused by the suction effect of the compressor. Superheating the refrigerant enhances both the refrigerating effect and compressor work. The coefficient of performance relative to the saturation cycle at the same suction pressure may increase, decrease, or remain the same. The process 3-4-5-6-7-8 illustrates the refrigerant's flow through the compressor. When the refrigerant enters at point 3, the pressure drops to point 4 due to friction and the suction effect, resulting in an actual suction pressure lower than the evaporator pressure. During suction and before compression, the temperature of the refrigerant vapor rises to point 5 as it contacts the compressor cylinder walls. Actual compression occurs between points 5 and 6. Similar to the heating effect during suction, there is a cooling effect at discharge, illustrated between points 6 and 7 in the diagram. Both heating and cooling effects occur at constant pressure. Due to frictional resistance, there is a pressure drop that keeps the discharge pressure higher than the condenser pressure. The process 8-9-10 shows the refrigerant's flow through the condenser. Process 8-9 cools the refrigerant from a superheated state to a saturated liquid, while 9-10 represents subcooling during condensation before it passes through the expansion valve. This is desirable as it enhances the refrigerating effect. Let's briefly explore the refrigerants that serve as working fluids in refrigeration systems. Refrigerants are chemicals that facilitate heat transfer in cooling systems. They are classified according to their environmental impact, safety, and performance. Understanding these categories is crucial for selecting the most appropriate refrigerant for an application, taking into account energy efficiency, global warming potential, and ozone depletion potential. Refrigerants. Classification based on chemical composition. Chlorofluorocarbons, CFCs. CFC refrigerants, such as R11, R12, and R115, contain chlorine. These were once commonly used but were banned in the early 1990s due to their harmful impact on the environment. Hydrochlorofluorocarbons, HCFCs. HCFCs, like R22, R123, and R124, replaced CFCs. While they also contain chlorine, they are considered less harmful to the environment, with lower ozone depletion potential, ODP. Hydrofluorocarbons, HFCs. HFCs, including R410A, R407C, R134A, R32, and R454B, do not contain chlorine and thus do not deplete the ozone layer. However, they have a greater impact on global warming compared to traditional refrigerants. Natural refrigerants. Natural refrigerants, like ammonia, R717, carbon dioxide, R744, and hydrocarbons, R290, R600A, are eco-friendly options with minimal environmental impact. They are gaining popularity as more environmentally responsible alternatives.